Welcome back to another GGTutoring video. Today I'll be covering the radical addition to alkenes. I like to think of this as like a very strange concept that got thrown at us just about movements of one electron. It's the way I like to think of this reaction. So I've written some key points to kind of think about when we're doing radical additions to alkenes that can help us start thinking about the problem and know what we're working with. So the first main thing is that what you'll see in most of these reactions, like general trend, is that it's anti-Markovnikov. It's not gonna be an addition to the most substituted carbon in this case, in comparison to the normal HX additions that we've done, like in the first chapter. Second is that you're going to see a mixture of anti and syn stereochemistry, as these radicals can add either above or below the plane. And this is how we observe both anti and syn stereochemistry. And for this reaction to even occur, it needs to occur at a rate much faster than the HX addition occurs at. And one of the main things to recognize when you know you're going to do a radical addition is seeing a peroxide. I've drawn the basic structure here, just an R connected to an O, two R's connected to an O, and those groups are connected to each other basically. And whenever you see HV or a delta, which is light and heat respectively, this will actually break up your peroxide into two equivalents, and which will allow you to actually initiate and start your radical addition to these alkenes. So basically in Chem 343 and like first semester Orgo, we've really been talking about double-headed arrows, as I've shown right here that I zoomed in on, which indicates the movement of two electrons. But now we're looking at these fishhook arrows, half arrows, which actually indicate the movement of one electron. It's very important you know which arrows you're using and what they mean, because this can result in loss of points and maybe not show your full understanding of the material. So it's very important that you understand the difference between these two arrows and what they actually mean. So with these key points in mind, I can move on to my first example. So first on the top, it's going to be an HX addition. So if you don't remember what that is, I'll just draw it out. So you have the electrons in the pi bond, which are going to come and extract with hydrogen and displace the bromine. And you're going to get a carbocation now, and you have a bromine. And this bromine can add either above or below into the plane, and you're going to get a mixture of products. So with this in mind, this looks very similar now to this next example, but you see that we have a peroxide on the bottom. So to even begin this reaction, let's say that heat or light was introduced. So we can just draw this again. Light's been added. This step is critical before you even do your radical addition to these alkenes. So when you add heat, you're gonna have a movement of one electron from each bond. There's two electrons in this bond, but one electron is going to go to one side, another one's going to go to the other oxygen, and basically split it up. I like to draw my one electron like a very darker and bigger circle, so I know for sure that's one electron. I don't confuse myself. You're going to get two of these, so we can just write two equivalents, because we made it twice, obviously. We have HBr as our starting material as well on the top. So basically what's going to happen is that this radical is going to extract one of the electrons from this HBr bond and then displace this bromine. And you're going to get an alcohol now, ETOH, plus a bromine radical. Okay? And now, so basically it's going to, so this pi bond is going to come in and form a bond, and one of the electrons in the pi bond is going to be displaced and put it onto that central carbon right there. And what's going to happen is you're going to see something that looks like this. Our bromine is going to attach here. And now we have a radical. This is electron deficient, missing one electron. But then we can get one more HBr that comes in. And this is going to come and form a bond with one of the electrons in that pi bond and displace that bromine. And then you're going to get something that looks like this. And you're going to end up with a bromine radical. Hope you were able to follow what I was doing here. I know it can be a little complicated with, especially with this HBr bonds, why we're taking an electron from the bond and not just having the electron go to the hydrogen and displace the bromine. That's because we're only involving one electron and not two. So we need to take one electron from the bond, which also implies that you're taking the hydrogen with it, while one of the other electrons goes into the bromine, basically. So if you didn't follow, I have one last example. A little bit more complicated, but it's going to be the same principles. So basically, a circle, and we have a T-butyl group up top, and then this peroxide with two T-butyls, basically. So it's a similar process. So let's say that we let's add heat this time, doesn't really matter. We're going to break up this peroxide, one electron going to either side, and you're going to form two equivalents. And now what's going to happen is, since we have HBr again, this is going to interact with our HBr, and then this one electron on the oxygen is going to come and extract the hydrogen. So one of the electrons from the bond has to come in, and then that other electron will go in and displace that bromine to make a bromine radical. Whatever you form here is just going to be an alcohol, but it's not really used anywhere else. The main thing is this bromine radical. So now that we have a bromine radical, we can go here now. I'm going to come in and take one of the pi bonds. And one of those other electrons left in that pi bond is going to go on to that carbon. And since this bromine can add either above or below the plane, it can either be dashed or wedged. So I'll draw it as a squiggly line. But we're not done because we don't want to have this one electron on our molecule, which makes it a little unstable. We'd rather have the radical on just one atom instead. And we know that we have more HBr, and this is going to come, take the hydrogen and one of its electrons, and displace that bromine. And then we're going to finish with our bromine radical, which we would prefer. And that's basically it, because we generated a radical already when we added light to this peroxide, so we need to end with a radical to kind of conserve what's happening in this reaction. And this is how we can actually add radicals to our alkene and make desired products. So that's really all I had for you guys today about radical additions to alkenes. So hope this video is helpful. I know it can be a little confusing, so definitely try and get some practice if you can. It'll definitely make this a little bit more simple. But if you have any questions at all, please feel free to drop them down in the comments below. I'll be happy to answer any of them. And I hope this video was helpful. So yeah, I hope you guys enjoyed, and stay tuned for the next video, guys. Thank you.